Now here we have an RLC circuit and we are required to find the VOT for t is equal or is greater or equal to 0. So the first thing that we have to do is to find the initial inductor current and the initial capacitor voltage. So before t is equal to 0, so remember when t is equal to 0, we have a closed circuit here and this part of the circuit is being disregarded, so we only focus on this part when t is equal to 0. So before that, this part of the circuit is being disregarded. We only focus on the circuit and on that circuit. So now that we're looking for the initial inductor current and also the initial capacitor voltage, we are going to disregard this part of the circuit since it's been disconnected to that circuit and that circuit. So to find the initial inductor current, we're going to focus on this part of the circuit since the inductor is on this part of the circuit. So remember, the inductor, when a circuit has been closed for a long time, the inductor turns into a short circuit. So which means that here we have a short circuit before t is equal to 0. We only have just the wire over there. And then remember, a short circuit, it has zero resistance, which means that current will go into this wire instead, into this inductor, sorry, and then this resistor will be disregarded, will turn into 0 because current looks for the easiest way to pass. So here there's 0 resistance, so the initial inductor current is actually that whole current, which is 5 volts. So the initial inductor current, so let's just say IL0 is equal to that current 5 amperes. So now we are going to focus on this part of the circuit since the capacitor is on this part of the circuit. So when we're looking at this part of the circuit, we have a capacitor right there which is 25 microfarads and a voltage source. So remember, the voltage here across this capacitor will be the same as this voltage. So the initial capacitor voltage is, let's say, VCO is equal to 100 volts, and we found the initial inductor current and initial capacitor voltage. Now we move on to our next step. So on our next step, we're going to focus on this part of the circuit. We're going to disregard this part of the circuit right now, and we're going to look at that part of the circuit. So the second step is to find frequencies. So let me write it here. Step 2, find frequencies. So what are the frequencies that we're looking for? We're looking for the damping frequency, so the Napa frequency and the radiant frequency. So the Napa frequency, which is like this, so it is equal to 1 over 2 RC, which is equal to 1 over 2 multiply that by the resistance. So the resistance that is across this part of the circuit, the circuit that we're looking that is active at the moment after T0, which is 50 ohms, multiply that by the capacitance, which is 25 times 10 to the power of negative 6, and that will give us the value of 400 radians per second. Now we have to look for the radian frequency, which is WO, which is equal to the square root of 1 over LC, and that is equal to, and also remember that we are working with a parallel RLC circuit, so this is parallel RLC. So when we are working with parallel RLC, we use this equation for the NEPA frequency. We use 1 over 2 RC, and when we are working with a series circuit, it's a different equation, which we'll look at next in our next example. So for now, let's just focus on this one. So for the radian frequency, this is equal to the square root of 1 divided by the inductance. So when we look here, we have the inductance of 160 millihenries. So we have 160 multiplied by 10 to the power of negative 3 multiplied by 25 multiplied by 10 to the power of negative 6 millihenries, and that is equal to 500 radians per second. Now that we have the frequencies, we have to determine whether we'd have to determine the response of our RLC circuit. So let's say step 3, determine the response. So how do we determine the response of our RLC circuit? So we compare the NEPA frequency and the radian frequency. So we're gonna say the NEPA frequency squared and the radian frequency squared. So when we square the NEPA frequency and when we square the radian frequency, we can already tell which one is going to be bigger than which one. So when we square this one, square that one, this one will be greater than the NEPA frequency. So we have the radian frequency squared is going to be greater than the NEPA frequency squared, and this gives us an underdamped response. So this is called underdamped response. So next up, we have to determine the damping frequency. So when we find out that our response for this circuit is underdamped, we have to find what is called the damping frequency. So we have, okay, step 4, determine the damping frequency. So the damping frequency WD is equal to the square root of the radian frequency squared minus the NEPA frequency squared. So we have the square root of the radian frequency is 500 and the NEPA frequency is 400. So we have 500 squared minus 400 squared, and that gives us a value of 300 radians per second. So from there, now that we have the damping frequency, now we have to find the variables, the constants of our equation. So let's do this. Let's say step 5. Step 5, finding the constant. So remember our equation for VO when t is greater than or equal to 0 is going to be like this. It's going to be B1 multiplied by e to the power of negative the Napa frequency multiplied by t cosine of WD t plus B2 e to the power of negative Napa frequency t, multiply that by sine of WDT. So we already have some of these values. We already have the Napa frequency, we already have the damping frequency. So we can put that into our equations already, or we can just go ahead and find the constants B1 and B2. So let's start with B1. So for parallel response, B1 is equal to the initial capacitor voltage VO, which is equal to 100 volts. We found that previously, which is 100 volts. So we already have B1. So to find others, so we're going to say there's another equation where we can find B2. So we have minus the Napa frequency multiplied by B1 plus the damping frequency multiplied by B2 is equal to 1 over capacitance, multiply that by minus VO divided by R minus initial current. So we can substitute whatever that we have into this equation. So we have the Napa frequency, which is minus with 400, and then B1 is 100 plus and WD, which is 300, and then B2 we don't know, and then 1 over capacitance. So the capacitance was 25 times 10 to the power of negative 6, multiply that by V initial, which is minus 100, divided by the resistance, which is 50, minus the initial current, which is 5. Now when we put that into our calculator and do our calculations, we find out that B2 is equal to negative 800. So now that we have B2, we have B2, we have B1, and we can just write our final equation. So we have VO is equal to B1 is 100 and e to the power of negative Napa frequency, which is 400 t cosine of the damping frequency, which is 300 t minus, this is B2, 800 e to the power of minus Napa frequency t and sine that shouldn't be there. Okay, sine 300t for t is greater or equal to 0. So this is our final answer.